Suppose E and F are independent events in the same sample space. So as soon as we see independent, we should say, oh, that's associated to something special. One particular formula, the intersection, both E and F happening, can be calculated as a product of E times the probability of E times the probability of F, that product there. So as soon as we see independent events, you should immediately connect, okay, it's this specific formula. There will probably be other things, other formulas, other stuff to worry about, but this comes into play, and only if we see independent events. So, okay, let's read the rest of the question. If the probability of E is 0.3 and the probability that F happens is 0.7, or you could say 70% or 7 out of 10 times, find the probability of E complement intersect F. Okay. So, what can we do? We've got a complement and an intersection. If we had a lot of complements, we might try and do some De Morgan's Law trickery. But I might say, okay, we're asking for probability of two events being intersected. One of those events is a complement. Have I ever seen that in any formulas anywhere? Yeah, actually we have. There's a formula we know that says the probability of any event, I'll just call it E for a moment, is the probability of the intersection E with some other event, plus the probability that E happens, but that other event doesn't happen. That is a formula I recognize that I know about. You got to dig back into your knowledge base and know all the formulas that you know. But that has event and a complement. Now, obviously, it looks a little different than the way we have it written, so we're gonna revise this. This is just the way I remember the formula, but we're gonna revise it. We'll say the probability of F is the probability of E intersect F plus, now E will get the complement. All right? So that's just replacing all the E's with F's and F's with E's there. All right? So this formula we're going to focus on because it has the thing we're looking for. All right? So, and hey, we know the probability of F. That's 0.7. Do we know the probability of E intersect F? We don't. They didn't tell us that, but they did tell us the events are independent. So, let's give ourselves a little more space here. We know we're missing the probability of E intersect F, but we know that's the probability of E times the probability of F. That's 0.3 times 0.7. Right? Now you say, well, okay, how do you multiply decimals? Okay, really quickly, how do you multiply decimals? Line them up like regular multiplication. Multiply as normal. Ignore the decimal points. Okay, 3 times 7 is what? 21. Okay? Now at the end, once you've done that, now worry about the decimals. You count. How many digits do you see to the right of decimals? So there's 1 7, there's 1 3, that's 2 to the right of the decimal point. So you take your decimal point as normal. Like normally 3 times 7 would be 21. And you move the decimal point to the left by 2 points. So 0.7 times 0.3 is 0.21. And that's the probability of E and F both happening. That's the intersection. So we can take that, put it up here, and we are almost done the question. Okay. 0.21 plus the probability that we're looking for, the mystery that we want to find. 0.21 plus that equals 0.7. Well, if we subtract 0.21 from both sides, we will have the probability we seek. 0.7 minus 0.21. All right, so now we're subtracting decimals. So you line them up so the decimal places are aligned vertically, and then subtract as normal. What's 70 minus 21? Right? Ignore the 0 points and everything like that. What's 70 minus 21? Turns out 49. So 0.49. So just under half, just under 50%, so 49% chance that when you run whatever the experiment is, F happens and E does not happen. So there's our final answer.